Greetings of the day. So greetings of the day to all present. So I welcome you all to this week 11 uh, discussion or problem solving session, doubt clearing or problem solving session. And the course, this is for the course EE116, which is being taken by Professor Debapriya called Fundamentals of Electrical Engineering. And I am Swastik Sharma. I am a TA for, I am one of the TA for this course. So yeah, let me share my screen. Okay, so today we are going to discuss today the topic of discussion is single phase transformer, in which we are going to learn how it works and what are the various ways in which we can analyze the circuit, and we'll see if time permits we'll discuss induction motor too. So let's start. So first of all, to give you a brief recap of everything that Sir has taught. Um, so when there is a, so for example, if there is a ferromagnetic core, just a second, yeah, I'm audible, right? Hmm. Okay, so yeah, so for example, if there is a ferromagnetic core like this, and if we wound coils on the both side of this transformer, right? So let's say we have some load connected to it, and this is N1, this is N1, this is N2. We are supplying a voltage V1, which is an AC supply. Um, and then what happens is when we supply when we give it an AC supply, there is a production of flux in both the coils due to mutual induction. And this flux links both coils, and with the assumption that um, the ferromagnetic core has infinite permeability. The flux stays confined to the core only, so there's no leakage of flux, and this causes a current I2 to flow at the second side, and the formation of V2 voltage with an induced voltages E2 and E1. Right. So this is how the circuit would look if we draw the equivalent. I mean, if we draw the circuit diagram, we can represent it something like this. So V1, right? Now, what happens is when we have a circuit like this and we supply it an AC supply, what happens is there's an induction of EMF, right? Which is represented as E1, E2. So this EMF is nothing but a product of Faraday's law and Lenz's law, right? This is due to Faraday's law of magnetic induction plus Lenz's law. Now, we all know what is Faraday's law of magnetic induction. It is the time rate of change of flux, right? and yeah, it's the time rate of change of flux, which when multiplied with the number of turns gives the induced EMF. And Lenz's law tells us that this induced EMF is in the opposition of the applied voltage, right? So Lenz's law states that whenever there is an application of something, the induced EMF will try to resist that application. So that's why a negative sign is there. Now, so if we talk about an ideal transformer which has, let's say, it has infinite permeance, no no leakage resistance or reactances, no leakage impedance, and what else put the assumption? Okay, let's leave it for here for now, right? So this infinite permeance means what? This infinite permeance means that the core has uh, has has negligible reluctance. When a core has negligible reluctance, what happens? The same case is with that of the same is with the resistance too, right? When there is negligible resistance, what happens? Maximum amount of current flows through that resistance, right? Similarly, if there is infinite permeance or negligible reluctance, the flux stays confined to that core only, right? That's what I mean by infinite permeance. Great. So this means that for this relation, that the flux will remain same for both of the coils, right? So which gives, therefore, E1 by N1 will be same for E2 by N2. That means induced EMF per the number of turns is same for both the coils, right? Now, since it's an ideal transformer, and I've said that there is no leakage impedance, so leakage impedance will I'll tell you more about it. Just assume that there is some leakage impedance, which how can we say that makes sure that the amount of current that is being supplied from the supply voltage is not being transmitted to the next to the is not being mutually transferred to the next coil, right? So, but since it has negligible leakage impedance, we can say that V1 upon N1, the whole supply voltage, is the induced EMF, right? Now, also we can have power balance too, right? Whatever the volt amperes is at the primary side will be the same at the secondary side too, right? So the volt amperes at primary side, because whatever we are supplying is being visible at the output too. I mean, the secondary side too. There is nothing. Uh, there's no way the power could diminish, right? It's the law of conservation of energy. So that means V1 I1 is equal to V2 I2. And we know V1 is what? V2 times N1 upon N2, which tells us that N1 I1 is equals to N2 I2, which leads us to this equation, which further means that MMF of primary side is equal to MMF of secondary side only for the case of ideal transformer. Okay, this is it. Let's jump to the no load operation of the transformer. So what do we mean by no load? That there is no load connected to the transformer. So let's take the scene. Now we say that it's open circuited, that is, there is no load connected to it. So there won't be any I2, right? No load is there. So what happens is there is still a flow of current, which is called I naught. This I naught is called no load current. So this current is responsible for providing the induction, or it produces the magnetic flux inside the core, right? So and it induces an EMF at secondary side, right? Hmm. So hmm. So yeah. Now let's try and draw a phasor diagram. No load. Now, since flux is same for both, we generally take it as a reference. It's a very good assumption to do this. So we have a flux phi, right? Now, what is happening? So we have an application of V1, right? So V1 is applied and then flux phi is produced, right? So hear me out. If I say that since it's responsible for setting up the current I naught and hence what is called hence the flux too. So V1 should lead phi, right? Because it's being applied first, and then there is a production of current which produces flux, right? So V1 leads flux by 90 degrees, right? Now, after V1 is applied, I naught is produced, which is in the same direction of flux phi, right? It's for an ideal transformer. Then after flux is produced, what happens is there is a production of EMF. There's an induction of EMF, right? An EMF is induced in both the primary and secondary coils, right? So that means after flux is provided, the EMF is induced. So we can write, so that means the induced EMF will lag the flux phi, right? So E1, E2, they lag. Now I can prove this to how E1 and E2 are lagging, right? Let's say, for example, we have a flux phi, which is nothing but phi m sine omega t, right? Now we know that the induced EMF is given by the uh, application of Faraday's law and Lenz's law, right? So E is what? Minus n d phi by dt. So if we do the differentiation, what are we left with? We are left with this, right? This term will come, and sorry, there will be an omega 2, right? Hmm. Right? And we can write this as minus n phi m times omega sine of omega t minus 90 degrees, right? We can do that. So, so this means that the induced EMF is uh, uh, it opposes the flux production uh, and it lags it by 90 degrees, right? That's how I've written this two terms. Now, since we are at it, we can also represent it. So this is what? This is the maximum EM, right? So we can write E is equals to, this is not visible. So we can write E is equals to EM sine of omega t minus 90 degrees, right? So EM is what? N phi m omega, which can be written as 2 pi f n phi m, the RMS value of which is, I should write it like this, instantaneous. So since it's instantaneous, I'm representing it by a small e. So ERMS is what? Or we can simply write E is 2 pi f n phi m divided by under root 2, which is what? If we do it, you can also do it with me. Root 2 times pi, right? So it's 4.44 phi m. right? So that's so we can write the RMS value of induced EMF is nothing but 4.44 times frequency times the number of turns times the maximum flux produced in the core. Right now, but there's one problem with this. So we have assumed that the whole no load current supports the formation of flux, right? Which is not the case usually. Usually, what happens, there are core losses too. Core losses in the form of, we have already read about it in our previous class, we talked about it. Whenever there is a production of flux, whenever in magnetic circuits, there is a production of eddy currents and hysteresis losses, right? So these are called core losses. So when I naught flows or the no load current flows, it not only produces the flux, it also produces these losses too, right? So we need to account for these losses as well. So that means our circuit will look something like this. Oh, sorry, the phasor diagram will look something like this. So it's very important for you to see how the phasor diagrams are being made, because it will help you in producing what you say similar diagrams for the for similar set of machines, right? Whenever you do questions. So yeah, this assumption is no more valid, right? So that means, let's say it's some I naught which is at a phi naught, which lags V1 by some phi naught angle, right? So what happens is the the y-axis component of I naught is called IC, and the x-axis component of what you say I naught is called magnetizing current. So IM is responsible because it's in the direction of flux. It's responsible for the production of flux, while the while IC is responsible for the production of core losses, right? So we can see, or we can write to that IC is what I naught time cos phi naught, and IM is I naught times sine phi naught, right? Which can also be written as, right? So this is how we write it. Now since I said that IC represents the core losses, so we need to know how to write core losses, right? So core losses are nothing but V1 times IC cos phi naught. So this is what a transformer on a no load, the phasor diagram for a transformer on a no load will look like, right? Now let's move on. So any doubts up until now? Let me see. So it's easy, right? Let's move on. So let's talk about on-load transformer. Let's on-load. So how will its operation look like? We'll use the similar. Oh, sorry. Hmm. So yeah. So this is how a transformer on a load will look like, right? But yeah, before that, let me discuss some. Hmm. Now I told you that this I naught can be decomposed in such a way that it will be that it will produce both the core losses and the magnetizing effect in the the production of flux in the magnetic core, right? So how will it look like if we say, let's say, for example, we wrote the circuit like this, right? It would look something, circuit diagram will look something like this. But if we have, let's say, these components, how do we represent it? Let's see. So let's say we're still not considering any leakage impedances, right? We have some um, I1 component, and then yeah, we have our primary winding N1 and our secondary winding, which is open circuited, right? So I1 is nothing but I naught, and this I naught goes through a resistance. So this is called RC, and this is called XM. So the current through RC is called IC. Yeah. So current through IC, just the current through this is IC, and through this is IM, right? And the current here is also I naught. So the whole current is being used to set up uh, this uh, this flux in the magnetic core, right? And core losses as well. So yeah, so now you must be thinking that why have I represented them by a conductance or a resistance? Because it's in shunt, let's say conductance and uh, a susceptance of 1 upon xm value, right? Now, as I've told you that I naught is lagging V1 by phi naught, right? Some phi naught um, angle. So since it's lagging, it must definitely have um, inductance, that's for sure. But since it's not purely lagging at 90 degrees, it must have some resistance too, right? So that's how I've differentiated both. And since we know that V1 times IC cos phi will produce, phi naught will produce what you say, this would be I naught. Yeah, I naught times cos phi naught will produce this core losses. So that's why I've represented it by RC. Since and then we can write it like, so the core losses can also be written as VC times IC or IC squared times RC. Both are equally valid, right? And the XM produces magnetic flux since it's an inductive coil, and that's why we represented by an inductive coil, right? Now let's move on and let's see how on-load transformer will look like with non-ideal characteristics having. We'll still consider infinite permeability. Let's leave it till there, and we'll say that there is some leakage components too. Right? Let's redraw the circuit. I've already. So I've assumed now that there is some leakage component too, and I'll talk to you more about why I have included it the leakage component too. But you must be hearing voices, right? Sorry for the trouble. There's some fest going on, right? So just hello. So I've create high. Okay, I've set the background noise suppression to high. Let's see if it makes any difference. Sorry for the trouble. Yeah, so I've added some leakage component to R2 JX2 and R1 JX1 with the load impedance too, right? Now, what do we have here? Like, for example, this is I1. Now, how do I represent this circuit? How do I draw a circuit diagram, right? So let's do it. Hmm. So how do we draw it circuit diagram? Now, so already told you when there is no load connected to it, there will always be this component, right? Irrespective of if there is a there is a load current flowing or there is a load connected or if there is no load connected, this shunt resistance in parallel with the this shunt reactance will always be there. So let's draw it. So we have primary side leakage resistance in series with primary side leakage reactance, shunt components. Okay. This is V1, this is I1, RC, XM. Great. So secondary side leakage resistance and secondary side leakage impedance connected with some load. This right. This would be V2. This would be I2. Right. So we have this right now. Yeah. So there will be I1 flowing, I not over here, IC and IM over here, and now we know that not the whole supply current will be being used to set up this load current, right? So the load current that is being set up is represented like I2 dash, which where I2 dash is nothing but I1 minus I naught, right? So this I2 dash is called as the secondary side, or the load component on the primary side, right? So this offsets the the load current on the primary side. So that's how we represent this, and this sets up the MMF and provides the constant mutual flux, which is independent of the load, right? So if we do what you say, K, so yeah, one more thing, induced EMF I haven't represented, E1, E2, right? So if we do KVL across primary, so how can we write V1? V1 can be written as E1 plus I1 R1 plus J times I1 X1. Similarly, V2 will be what? Can anyone tell me? Simple, right? Okay, it's E2 minus R1 plus J2 X1, right? So, so we got these three equations, and we know about the no load current, right? I naught. So we don't need to write specifically about it right now. So let's see how its phasor diagram will look like. I'll draw it on the separate page. So in this too, we'll take since phi is same for both, we'll take it as reference. So flux is taken as reference, right? Now I naught is the one that's helping set up this flux, right? So we know, but it doesn't coincide it or isn't in phase with this I naught. And we also know that even in E2 will always be opposite to that. Sorry, will be lagging the flux by 90 degrees. Now, let's talk about E2 first. So we know that since the secondary side is inductive in nature, it will lag, right? The I2 current will always lag. So, so the I2 is lagging. We know this, right? Should represent it. Now, in the second equation, you can see that it's written E2 minus I2 R1 plus J times I2 X1, right? So, uh, if we want to write it like this, how can we uh, to say, yeah. So I was yeah. So I was saying that how can we depict this on the phasor diagram? That's the main motive that we want to do right now. So we know that this I2 is lagging the voltage V2, right? It will always do that. So it can be represented like something like this. Since it's J times I2 X, oh, sorry, should be R2. So it's written J times I2 X2, right? So this is I2 times X2, right? And we know I2 times R2 will be something like this. And the phasor representation will be something like, so this would be our V2 phasor. So that's how V2 will be represented, and it's the current is lagging it by some phi 2 phase angle difference. Now, we know that one more thing, forgot telling you, this I2 dash is setting up the MMF, right? So N1 times I2 dash is equals to N2 times I2, which can be written as N2 by N1 I2, right? So that means since, yeah, if we take the dot notation, for example, so I2 dash is entering and I2 is leaving, right? So I2 dash and I2 will be in anti-phase to each other. We know when the how the law of magnetic induction works. So I2 dash and I2 are anti-phase in each other. That means they are separated by 180 degrees difference, right? So I2 dash can be represented similarly. So this is I2 dash. Now I know I2 dash plus I naught will give us what's called as I1, right? So let's do it. So this is I2 dash, and this is our I1 current, right? Okay. Now we know that how is V1 represented? V1 is represented through this equation, E1 plus I1 times R1 plus J times I1 X1, right? Now if we take a negative, so this is negative E1, right? Okay. Now we know that, yeah, phasor addition of E1, I1 R1 and I1 GX1 will give us V1, right? Let's do it. So we know the I1 R1 will be in same. Yes. This is I1 R1. This is I1 R1 perpendicular to it. I1 X1. let's extend it so that it's bit. I1 R1. So somewhere here, this is V1, right? And the direction, this is phi1, and the I1 will lag V1 by phi1. So that's how you draw a phasor diagram for an on-load transformer. Now it's equivalent. Let's talk about equivalent circuit representation. So any questions up until now? Fairly simple, right? Okay, let's move ahead. So let's draw equivalent circuit representation of a transformer. Okay, so we already drew this. Let's go over there. Hmm. Right, this was our circuit. Now, what we want to do is we want to draw the equivalent circuit only from the primary side, right? Let's draw everything, the secondary side components, let's take it to the primary side. So what are the components over there? So we have R2, X2, and some load. Let's say that the load impedance is RL plus JXL, right? So we want to take it to the primary side, or draw an equivalent primary side. So we know, let's say that there is some R2 dash at the primary side that I2 dash will be getting to, right? So the copper loss, sorry, the power dissipated in that resistance would be equal to when what is being dissipated at the R2 resistance at the secondary side, right? So we know I2 dash is what? N2 by N1 I2. Let's represent it. N2 by N1 square times R2 dash is equals to R2. And N2 by N1 is nothing but, we can call it as, so N2 by N1 is K, right? Or 1 upon K, sorry. So R2 is nothing but, R2 dash is nothing but K square R2. Similarly, X2 dash can be written as K square X2. R load dash can be written as K square RL. And XL dash can be represented as K square XL, right? So let's redraw it. So how would it look like? There is some resistance R1, G times X1. R2 dash, dash. Right, so we have this, and we know this is V1, this is I1, right? So that's how we represent. We have an equivalent. This is called an equivalent circuit representation of a transformer, referred to the primary side. So in the similar way, we can refer everything to the secondary side as well. Um, I leave that task to you. Okay, so what else? Let's talk about losses. So we said there are core losses, iron losses, or copper losses, right? So a copper loss is represented by, so Cu loss, let's say. So this copper loss is what? I1, sorry, first I need to. So this is generally how we represent our transformer, right? There is one more representation. We the shunt circuit into account, right? So how will we write it? It will be something like this. So this is called approximate circuit representation, right? Okay. Now I want to talk about losses in a transformer. So whatever is supplied from the supply voltage or the supply side doesn't get converted to output. That we all know, right? There are always losses in any circuit. But since this circuit, the transformer is static in nature. I mean, it doesn't have any dynamic or moving parts. So its efficiency, or we can say losses are less, and the efficiency is very high. But still, it still suffers from losses. So let's discuss about it. So first, the copper loss. So copper loss is, if I want to write it, for an exact, let's say for an exact circuit, how would be represented? For an exact equivalent circuit, VCU is I1 square times R1 plus I2 dash square times R2, right? The This is how the what you say, yeah, how this is how the copper losses will look like. So let's say that uh, yeah, so sorry. Hmm. What do I exactly want to discuss? Hmm. Just for example, so yeah, I should have, yeah. But for an exact circuit, what happens is, right? So I1 square is nothing but I2 dash square, right? It stays the same because for an approximate circuit, the I1 and I2 dash are the same thing, right? So how would it look like? R1 plus R2 dash. This is sometimes called, or this is, yeah. So this is sometimes called um, uh, this thing is called equivalent resistance transfer to the primary side, right? So the copper loss is, we can write it like this, times Re1. Or the same thing, if we transfer the whole thing to the secondary side, can be written as PCU times I2 square into Re2, where Re2 is nothing but resistance Re1, sorry, 2 plus uh, R2 plus R1 dash, right? So where Re2 is the equivalent resistance referred to the secondary side. Okay, so this is how we can represent our copper losses too. So this is one way. Hmm. Now let's say that um, our transformer is not currently, what you say, our copper, the transformer is not operating at the full load, right? It's not supplying the full load current. So X is the ratio of the load current to that of the full load current, I2 upon I2 times FL. So copper loss can be written as X square times WCU, right? Where this WCU is nothing but full load copper loss. Hmm. Right. So that's how we can denote. Let's say you are given that currently the transformer is supplying 90% of its full load value, right? So and the copper losses at the full load are given. So you can easily calculate it would be zero point 0.9 square times the full load copper loss. And similarly, yeah. So let's talk about how efficiency would, moreover, there's one more kind of loss called as core loss or iron loss. So as I told you, I naught will be set up in the what you say in the transformer, irrespective of whether it's on load or no load, right? We know because I naught is needed to set up that flux. So the iron loss or core loss stay put, right? For example, they stay constant, they don't change. Load current, and generally we write it like V1 times IC, right? Or V1 times I naught cos of phi. Always remember this. Okay, now let's talk about efficiency. So we know output of transformer, let's say it's operating at some phi naught, uh, at some cos phi times power factor. Let's say it's operating at cos phi naught, sorry, cos phi PF. So the output would be V2 times I2 cos phi, right? That's how its output is going to look like. Let's say this I2 is not that full load value. So how would we written it? We can represent it as V2 times I2 times FL cos phi, where sometimes this V2 times I2 FL is the full load or the rated value of the transformer. Always remember, right? And this thing is nothing but full load DL power. So X times PFL. Now input to the transformer is this XPFL plus the copper losses that we are supplying and the iron losses, right? Always. And since it's at some, it's operating at a derated value, it's X square times the that of the copper losses. So efficiency can be written as output of transformer upon input of transformer, PFL upon X square. Now, for eta max, the condition for eta max I'll let you find it out. What you have to do is just differentiate it with respect to dx and equate it to 0. The condition comes out to be that the iron losses have to be equal to that of copper losses. Always remember. And at this point, the efficiency is maximum, which is given by time PFL upon plus 2 times 25, right? So this is it. What are we left with? Okay. Voltage regulation. Hmm. So for voltage regulation, what it means by voltage regulation? Like for example, when the loading increases, the terminal voltage at the terminal voltage at the secondary side starts to dip, right? It goes from some no load value to a full load value. So as the current goes from the no load to the full load value, this is called as voltage regulation. And generally, this voltage regulation is very minuscule. I mean, it's very small, but and in the smaller the better. I mean, yeah. So how do we represent it as VR, which is represented in percentage, no load minus full load upon full load. So this is how our voltage regulation look like, right? So yeah, so there are three cases which sir has taught. I'll ask you to please, yeah, we'll solve one question on it and then I'll show you how to do it. So let's move ahead. So there's one more concept, open circuit test. So some testing to derive the parameters of the transformer. So in the open circuit test, this is generally used for a determination of shunt parameters. And what exactly do we do in this test? Let's see. Let's say we have some supply side some transformer which has a voltmeter and an ammeter connected to it in addition to a wattmeter, right? So and we supply it with the load supply voltage at the LV side, and we keep the high voltage side open. Now what happens? These three things will show some value, right? Now I've already shown the ammeter. When the secondary side is open circuited, what happens? I've already told you. No matter if it's open side, there will be flux set up in the transformer, and to set up that flux, a no load current will flow, right? So the ammeter measures I naught, which is the no load current. The voltmeter measures the voltage of the supply side. And there is a watt meter. Now, this watt meter, what does it measure? Now, for example, when there is only the no load current flowing into the transformer, only the iron losses or the core losses will be there, right? There will be no, the copper losses will also be there, but since I naught is very less, the copper losses will be very small. So it would majorly show you the iron losses, core losses. Right. So I'm sorry if my speed is fast because I have to show you sample problems too. Okay, so iron loss is given by, we know, V1 times I naught cos phi, right? So we know this, we know V1, we know I naught. So cos phi naught can be found out, right? Easily. So cos phi naught will be V1 I naught, right? Since this is known, sin phi naught can be known, which is nothing but under root of 1 minus cos square phi naught. Now, if this is known, we can calculate IC, which is I naught cos phi naught, and IM, which is I naught sin phi naught. If this is known, we can calculate RC, which is V1 times upon IC, and XM, which is V1 times, right? So that's how we can calculate the shunt parameters through an open circuit test. There's one more test which is called as short circuit test. ठीक है. So this short circuit test is used to determine the what you say uh, the series parameters of the transformer, right? So here as well, there is an ammeter, wattmeter, and a voltmeter connected like this. The supply side voltage is very small. It's very small, and so VSC would be what? Sorry. So voltmeter will show us the VSC. Here, this VSC will be shown in the voltmeter, which is the supply side voltage. Always remember, open circuit test is conducted at the low voltage side, and the high voltage side is kept open. Whereas a short circuit test is conducted on the high voltage side, where the low voltage side is short circuited. Great. So voltmeter measures VSC, which is the voltage supplied. Right. Let's talk about ISC first. So ammeter measures ISC. Now, since it's connected directly to that of the it's connected near to the coil, right? The secondary primary side coils. It measures the full load current because since the low voltage side is short circuited, the current that is being induced at the low voltage side will show the effect on the primary side as well, right? So this IAC is the primary side equivalent of the full load current. Since full load current is flowing, the copper losses will be prominent, and the watt meters will measure the copper losses. Right. So what is resistance here? Resistance can be written as WSC upon ISC square, right? And we know Z is what? ESC upon ISC. We know this as well. So we can get impedance, this series uh, reactance, which is under root times Z square minus R. Right. So this is how you can calculate the series parameter using a short circuit test. Now, one more topic I have to discuss, and after that we'll solve questions. So let's discuss auto transformer. So I showed you through these diagrams that a transformer magnetically transforms the supply side value or the supply power to that of the secondary side, right? So it takes the power it is being supplied at the primary side and magnetically transfers it to the secondary side, right? But in auto transformer, there is there is a transfer of power magnetically, but also electrically. That means that some of it is transferred magnetically, while while some of it is transferred by a direct connection to it. So what do I mean by that? Let's say I have a coil, right, with some N1 turns, and I am supplying it V1. But now I tap it in between, let's say here, and take this value where it's some N2 turns. We get some V2 voltage with I2 current. So I1 is flowing over here. Here I2 minus I1 will flow. This whole thing is N1 and this whole thing is N2. So the VAs from this coil will magnetically link with that of this coil, right? But in addition to that, the VAs from this coil will also come into the picture too. That's it, right? So why is it used? I mean, what's the fun of it, right? So the applications are certain. It is used as a variac. You can tap it anywhere between the whole coil, and you can change the amount of voltage produced at the secondary side. It's called a variac, or a variable AC voltage. It is also used in induction motor starter. When we discuss induction motors, remind me and tell you where and how it is used. Right. So let's compare. So what's the difference between this and a two winding transformer? Right. We discussed both. So for an equivalent two winding transformer, let's say that the equivalent two winding transformer is nothing but this side and this side, right? I'll draw it with blue and red so that it's. So this is how an equivalent two winding transformer would look like. It will only link magnetically, right? Whatever is being linked magnetically, that's what I've shown. So this is N1 minus N2 turns, and this is N2 turns. This is V1 minus V2, and this is V2. Some I2 current, some I1 current. So for this equivalent transformer, what do I want to do is, I want to see how we can take parameters from one transformer and use it for advantage for us to derive how the parameters for the second auto transformer will look like, right? Hmm. Right, let's see. So we know for an equivalent two winding transformer, how will the voltage ratio look like? Sorry, turn ratio look like? It's nothing but V1 minus V2 upon V2, or N1 minus N2 upon N2, right? But for an auto transformer, K dash will be V1 upon V2, right? Because there are two things happening. It's linking magnetically as well as inductively because of this N2 coil 2, right? So it's simply V1 upon V2. So if we do it like this, V1 minus V2 plus V2 upon, we can say that it's nothing but K plus 1. So K dash is K plus 1. So for an auto transformer, the turns ratio is given by the turn ratios of that of the two winding transformer added with 1. That's what it is. Now, let's say let's talk about volt amperes, right? For a two winding transformer, it's given by V1 minus V2 times I1, right? That's how VA will be given. And for an auto transformer, it's nothing but V1 I1 or V2 I2, right? Now, consider this. So I can rewrite this as, right? I can do this. So this will give me 1 minus V2 upon V1, which is nothing but 1 upon K dash, right? Which can also be written as K dash minus 1 upon K dash VA auto, which is K plus 1 minus 1 upon K plus 1, right? So can be written like this. Always. So that's how you manipulate. That's how you get from an equivalent two winding transformer the parameters for that of the auto transformer. Okay, so we've discussed the theory for a single phase transformer. Let's discuss questions or some sample problems. So we've given this question. It says that we have a two single phase transformers A and B. They are supplied from a 215 volt 50 hertz source and a 430 volt 60 hertz source respectively.
Okay. So, एक minute.
No.
So we are starting from this question. We will be finishing the previous assignment.
Nagesh, you're unmute. So can yeah. Yeah, so we are given so that the cross-sectional area of transformer A and transformer B is given. And we are given that both of them operate at similar flux density, that is 0.75 Tesla. And we are also given that the number of turns for transformer B is 300. That means the primary side has 300 turns, which and we can take that of the secondary side as 1 only. So it's 300:1. So we are required to find the total number of turns of transformer A. So how will we do that? Let's see. So we are given area of cross section for the eighth transformer, which is 1.5 centimeter square. AB is given by 3 centimeter square, and B is given by 0.75 Tesla or Weber per meter square, right? Now we know B, right? So we can get flux phi A and phi B. So phi is what? 0.75. So B times A. So we can calculate phi A. Phi A comes out to be 0.75 into 1.5. Since it's in centimeter square, we'll divide it by 10⁴. We get 1.125 into 10⁻⁻⁴ Webers. And phi B is 2.25 to 10⁻⁻⁴ Webers. Right. Now, since we are given NB, which is 300, we can calculate the induced EMF EB, right? Let's say at the primary side we are trying to find out, right? So we know it's given by 4.44 times frequency times maximum flux produced and the number of turns. So what does it come out to be? It comes to be, since frequency is 60, phi B is given as 2.25 into 10⁻⁻⁴, and NB is 300. So we get 17.982 volts. Now we know EB is being excited with 430 volts voltages and EA is being excited with the 215 voltages, right? So EA will be, and since the flux produced, we know the flux density is same. So EA will be EB by 2, right? Which is nothing but 8.991. So we know 4.44 times EA is equal to 4.44 times frequency into phi into NA. NA is nothing but 8.991 divided by 4.44. Frequency operation is 50. Phi is 1.125 into 10⁻⁴. So if you find this out, what is it going to be? 360. So we got NAS 360. So it's C. Right? So that's how you solve this question. So any trouble up until this point? Okay, let's move ahead. Sorry. So we have this question. Yeah. So remember, I told you we'll discuss voltage regulation here. So we're given that a negative voltage regulation for a single. Yeah. Hmm. So remember, I told you we'll discuss it over here. So voltage regulation, I've already told you it's nothing but it's voltage is V2 at no load minus V2 at full load upon V2 at full load. This no load is nothing but E2, right? If there is no load connected to it, it's simply E2, right? The induced EMF at the secondary side. So let's talk about first unity power factor. So if we have a unity power factor load, let's say we have, okay, let me take this, okay. Right, let's say we have transferred every component from the primary side to that of the secondary side. So the equivalent resistance will be like I2, C2, and some load, which is a UPF load or a unity power factor load. All right. So this is E2, which is equals to V2, 0. And this is V2. For a unity power factor load, look at the that of the look at the secondary side. So if we draw the phasor diagram, how is it going to look? Let's take V2 as reference, since unity I2 will be in phase with V2, and since I2 is in phase with V2, I2 R V2, I2 XC2, and this is E2 delta, right? Now for this circuit, let's say that the angle, yeah, let's say the angle delta is, instead of doing that, so let's say what is E2 cos delta going to look like? So if E2 cos delta is superimposed with this, it's nothing but V2 plus I2 times RE2, right? That's what it will look like. Right? Now for small angle approximation, delta is equal to 0, cos delta will be equal to 1. So therefore, E2 is equal to V2 plus I2 RE2. E2 minus V2 is given by I2 RE2. If we divide both sides by V2, right? So that means, so this is nothing but voltage regulation, VR. So which means VR is equals to I2 times RE2 divided by V2. So can this ever be negative? No, right? This can never be negative for a unity power factor load. So that means C is not the answer. Now let's check for other kind of loads. Lag in PF. So if there is a lagging power factor load, again take V2 as reference. I2 lags by some 5, right? So this is I2 RE2. This is I2 XE2. And this is E2, right? So we got this, right? Let's assume this delta is very small, right? So first of all, this is nothing but I2 RE2 cos phi, right? And this thing, this is what? This is 90. This is 90 minus 5. This is also 90 minus 5. This would be I2 times XE2 sine phi, right? Because cos of 90 minus 5 is sine phi. Again, if I write E2 cos delta, it's nothing but V2 plus I2 RE2 cos phi plus I2 XE2 sine phi, right? Use small angle approximation. E2 will be V2 plus I2 RE2 cos phi plus I2 XE2 sine phi, right? So E2 minus V2 upon V2, which is VR, is I2 RE2 cos phi, I2 sine phi upon V2. Again, this can never be negative, right? Because both are in addition. So this is also wrong. One more thing I'd like to discuss is that the base impedance ZB is nothing but V2 upon I2, right? The rated value of voltage and the rated current or the full load current, right? Full load voltage upon full load current. So if I include this here, it would be ZB cos phi plus XC2 upon ZB sin. This here, RE2 upon ZB and XC2 upon ZB are called per unit resistance and impedances. Per unit. These are per unit quantities. So this is how you represent lagging for lagging power factor loads. Right. Now let's see it for leading power factor. What's left? A lot to cover in it. Yeah. So this is V2. This is I2 leading it by 5. Right. So again, similar thing. Since it's leading, this is I2 RE2. This is I2 XE2. This is our E2. And this will be delta. So E2 cos delta can be written as V2 plus I2 RE2 minus, sorry, cos phi, because this is phi, since this is 90. So this would be minus I2 XE2 sin phi, right? So if we do small angle approximation, this becomes E2 minus V2 upon V2 RE2 PU per unit cos phi minus XE2 PU sin phi. And as you can notice, if the per unit value of reactance is greater than that of the RE2, and the power factor is in such a way that it makes it become larger, the whole quantity larger, the leading power factor can have negative voltage regulation. And not just this, if you look at it in this way, since a negative voltage reaction regulation will have the current lead the voltage, right? It will do what? It will help in production, it will help in strengthening the voltage at that terminal. And it may so happen that the terminal would have a high voltage as compared to that of the voltage at the primary side. So this is sometimes called as Ferranti effect, and it's possible in cases where there is capacitive load connected, and capacitors have leading power factor loads or leading power factor loads. Okay, this is done. Let's move on to next question. So in this question, what we are given is we have a 220 volt, 210 volt, two winding single phase transformer, which is to be converted to a auto transformer, which is to supply power at 110 volts from a 330 volt source. Determine the kVA output of the transformer. So now we know, we have already calculated VA auto is given by what? K by K dash, or K dash by K, VA, two winding. So K dash is what? 3 by 1, right? So it's 3, and K is 2, right? This is K dash is 330 by 110, which is 3, and K is 220 by 110, which is 2. So VA of that is 1 kilovolt ampere. So that means it is 1.5 kilovolt ampere. So the answer is A. Right? It's an easy question. So any doubts until now? If you have doubts, you can always unmute yourself and let me know. Let's move ahead. So 100 kilovolt ampere, 12.66 kilovolt, 440 volt, 50 hertz single phase transformer has 18% impedance. So 18% impedance means the Z value is in per unit, which is 0.18. The leakage resistance referred to the low voltage side, that is the secondary side, is 0.3. Find the percentage voltage regulation of the transformer when it is connected to 0.6 leading power factor load. Okay, so what are the known things? Per unit value is given, which is 0.18, and we are given that the leakage reactance transferred to the secondary side, which is RE2, is nothing but 0.3 ohm, and cos phi is also given, which is leading, 0.6 leading. So what are we required to find? We are required to find the, what to say, voltage regulation. So for that, we need the base value, right? ZB is what? V2 upon I2. V2, and since we are given 100 kilovolt S, so we can write S upon V2, which is nothing but V2 square upon S, which comes out to be 440 squared upon 100 into 10 raised to power 3. The value of which is 1.936 ohms. So Z base is given by 1.936 ohms, right? Now, per unit value of the uh, secondary side referred leakage resistance is given by 0.3 divided by 1.936, comes out to be 0.155. Okay, so we are given ZPU, which is 0.18. So what is XPU? It would be simply ZPU squared minus RPU squared, right? So if you calculate, it could be 0.18 square minus 0.155 square, which is 0.0916. Let's see. Right, so we have all the values. Now, we know for a leading power factor load, the voltage regulation is given by this. If we find it, it's going to be 0.1155 into 0.6 minus. So if cos phi is 0.6, sin phi will be 1 under whole root square root of 1 minus 0.6 square, right? Which will roughly come out to be 0.8. So it would be 0.0916 times 0.8. So this value is what? 0.6 minus 8. This comes out to be 0.019732. 100%, which is nothing but 1.973 or 1.97%. So the answer is close to A, right? So the answer is A. So that's how you solve these questions. These are pretty straightforward if you see, right? Now let's continue. Okay, so we have this question here. Open circuit test and short circuit test is conducted, and we have a 5 kilovolt ampere 440 volt by 110 volt transformer, 50 hertz transformer. We need to find the magnetic reactance. So as I told you, only the open circuit test helps us in finding the magnetic or the shunt parameters, right? So we know Wi is given, which is 10 watt. I naught is given, which is 0.1286. V1 is given 110 volt, right? So XM is what? V1 upon IM, which is I naught sin phi, right? So let's yes. So we need cos phi, right? First. So we know V1 I naught cos phi is equals to 10. So cos phi comes out to be 0.707. Sin phi naught will be 0.7. Oh yeah, because it's 1 by root 2, right? Sorry. So we can easily find this out. This is 110 upon 0.1286 into 707, which is 1209.34. Okay, in kilo ohms, yeah, it's 1.21209 kilo ohms, right? It's near to this value, so D. See, these are pretty straightforward questions. If you know what the open circuit test does, you can easily calculate the parameters from that, right? So if there are any troubles, let me know. I'm sorry, the pace is fast because I have to complete this and start induction water, hopefully. Okay. So in this question, we were required to use only open circuit, right? But now, open circuit test. But now it's asking the kVA loading at which the transformer will give us maximum efficiency, right? So, so copper losses are only known in short circuit test, right? So we can see, um, so R1, okay, 1 second. So this was conducted on high voltage side, and this is conducted on low voltage side, right? No, sorry. Yeah, high voltage side. So that means the short circuit test is the HV side is our primary side, and let that LV side be our secondary side. Okay. Now, the short circuit test will give us the primary side equivalent resistance, right? So what is it going to be, since the 16.5 divided by 20, yeah, 10.3 squared, right? So what is it going to be? 0.155 ohms, right? So, and we know I1 primary side current is nothing but 5 into 10 raised to power 3 divided by 440. High voltage side is the primary side. So this would be 5000 divided by 440. So this I1 is our full load current, right? That's what I'm trying to calculate. So 11.364. So I'll tell you why. So for maximum efficiency, what we need is maximum efficiency happens when Wi is equals to x square times WCU, right? Now x is what? Wi times WCU. I can't straight away use these values because they are conducted at different loading, right? So I have to first convert it to a single loading side or for the whole transformer. Since this is conducted at 20 volts, but the high voltage side is at 440 volts. So I'm converting all of those values to a proportionate amount of the 440 volt side. But this here is conducted at 110 volts, which is what the low voltage side voltage is. So, but since this is the short circuit test is conducted at 12 volt, 20 volts, I'm trying to convert everything to that of 440 volts, which is the full load value of that, or the rated value of that voltage, right? Yeah. So this is what comes out to be. So now we know WCU will be what? WCU will be 20 watts. That's what the full load value of the copper loss will look like. So X is what? Wi upon WCU. Now Wi is 10, WCU would be 0.707, right? Hmm. So we got X. Now we need to calculate it with the maximum efficiency, right? So what is it? So eta max is nothing but X time, yeah, or it's nothing but eta max. So maximum loading is happening at 0.707 X, right? We can simply multiply it by the rated value. So which is nothing but 3.535 kVA. A is the correct answer. So you got it, right? So what we did, we converted everything. So the full load value of the copper losses, which is 20 watts, and we got X from it. And we know if we derate it by something, if the full load value is derated by something to give maximum efficiency, we can use it for similar purposes, right? To calculate the loading at which the maximum efficiency will have. Okay, so we have, hmm. Okay, so in this question, the similar transformer with the similar open circuit test and short circuit test is given. We are required to find the percentage efficiency of the transformer at 90% of full load at 0.6 lagging power factor, right? So we know we calculated. So I2FL will be what? 5000 upon 110, right? This is 45.45 amperes. And we are given that the load is lagging power factor, which is 0.6 lagging, right? Now, what we are required to find is, so if this is I2 will be what? X times I2 full load, which is what? 40.91 ampere. We got this relation. Now we know the full load power will be SFL times 0.6, which is what? 3, right? and X time PFL will be the one that's happening at 90% of full load rate, which is 2.7 kilowatt. So we got everything. Now we are required to find what? We are required to find losses. So iron loss is given by 10 watt and copper loss. So the full load copper loss is where? What? It's 20 watts, right? That's what we're required to put over here. Multiplied with X, which is 0.9 times 20, which is 18 watts. So we have everything with us. Now efficiency is what? 2700 divided by 2700 plus 10 plus 18. X squared, sorry. 16 point. So if we find the value, it would be 0.9904 or 99.04%. So the efficiency comes out to be 99.04%. And since none of the matches, the answer is none of the above. Right? You can see these are pretty straightforward. You just have to know what these values are and you can calculate these quantities. So any doubts up until now? So we'll move ahead. So we have this question. Here, a 440 volt, 110 volt, 5 kilovolt ampere, 50 hertz single phase transformer, which has a maximum efficiency of 99.44% at 5 kilovolt ampere at unity power factor. During the day, it is loaded as follows. Find the all day efficiency. Okay. So we know at maximum efficiency what happens. Wi is equals to WCU, right? So we can make use of this expression or this equivalency and find out that 0.994 times, since it's at unity power factor, right? So we can calculate 2 times Wi is what? Settle into power factor divided by eta max minus this. So if you find out this expression, what is it going to look like? It will be 9.44 divided by 2. So 0.01407 kilowatts or 14.07 watts. Right. So we got this, and we know copper losses are the same thing. These are also 14.07 watts. Okay. Now we know iron losses will stay the same for the exact 24 hours, while the copper loss will change uh, depending upon the loading that's being given to it, right? So how do we do it? Let's create a table. So for first 6 hours, what's happening? We have 1 kilowatt of load at 0.6 power factor lagging, right? So that means S is what? 1 upon 0.6, which comes out to be 1.67 kVA, right? That means X is what? So X comes out to be 0.33, right? 0.33. Right. So copper loss is what? 0.333, right? So it's 0.33 squared times 14.07 watt, right? So if we n multiplied by 6 because it's for 6 hours, so this comes out to be 28.14 watt hour. Next 4 hours. So what do we have? We have 5 kilowatt at 0.8 power factor leading. 6.25 kVA. 1.25, which is 1.25 times into 4. 4 hours. So this comes out to be 87.94 watt hours. Next 14 hours, right? 14 hours. So S is what? 4 kilowatt at 0.95. Okay, so for 24 hours, total copper loss is what? 28.14 plus 139.65 plus 87.94, which is nothing but 2255.732 watt hours. And total iron loss, it's simply Wi times 24, which comes out to be 07 into 24. 337.7 watt hours. Right. Now, this is what our total loss will look like, and total power output is 1 into 6, which is 6,000 plus 5 into 4,000, sorry, 5,000 into 4. Just a second, I'll do it like this. 6 plus 20 plus 56, right? So this is 6 plus 20 plus 56, 82. So it's 82,000 watt hour. So we need to find efficiency of all day, right? 82,000 divided by 82,000 plus 255.73 plus 337.7. It's 0.9928 or 99.3% efficiency. So we're getting 99.3% efficiency, which is D, right? So that's how you solve this question. Pretty straightforward. There's nothing, there's just calculations, right? So one more question, last question. So in this question, what we are given is we are given a single phase 1 kilovolt ampere 220 volt 110 volt two winding transformer, which has an efficiency of 92% at full load, unity power factor. If it is reconnected as 330 volt 110 volt auto transformer, its efficiency at its new rated load at unity power factor will be. Okay, we can do that. So we know for two winding full load is given by 0.92, right? Yes, we know. And the full load KVAs are 1 kilovolt ampere, and we know the value of K is 2, right? Similarly, for K dash is 3, right? Now we need to find out the efficiency at its new value. Now, how do we? So first of all, we'll calculate the losses, right? The losses will stay the same irrespective of it, how it's being transformed to what it's being transformed. The losses will stay exactly the same, right? So eta is given by SFL into PF upon SFL into PF plus losses, right? So the losses come out to be SFL into PF. What is it? It's 1 upon 0.92 minus 1, 0.869, right? These are our losses, kilowatt. Okay, so the new, and now we know also, this is, should write it like this. So S for auto transformer at full load, I've already told you the expression is this, right? K dash upon K times V. So it's K dash upon K times W. So what is it? It's 3 by 2 times 1, which is 1.5 kVA, right? So eta for auto transformer will be 1.5 upon 1.5 plus 0.0869. This comes out to be 0.9452 or 94.52%, right? Let's see. So what we did, so as I solved this question, I got to know that we can find losses, right? Efficiency is given. We know the power. We know the power factor. We know the kVA of the trans the what you say the two winding transformer, right? Would be multiplied by power factor, which is unity only. Still, I'm writing so that you don't get confused, right? So we know the kVA of two winding transformer at full load, which is 1. We know the power factor is unity, and we got the losses. Now we know how to get the VAs of auto transformer from that of the two winding transformer. We did that. We got the VAs for that auto transformer, and from that we calculated the efficiency, which is nothing but the power at full load for the auto transformer divided by the power of full load plus losses. So that's how you solve this question. So to solve this question, so first, whatever's written on there, try to gauge what you can get from that, right? Since efficiency was given, I just simply wrote the formula for efficiency. I got that I need to figure out what the losses are going to be. From that, I knew if I got the losses, I know the power for the auto transformer, and I can get the efficiency for the auto transformer too at the same load. So that's how you solve this question. So today we discussed everything about single phase transformer. I'm sorry, so I couldn't find time to discuss induction motor. So we'll discuss it in the next week, and we'll solve some sample problems related to that. If you have any questions, I'm open for them. Okay, since there are no questions, we'll end this class. So I hope you have a great rest of the evening. Thank you so much for joining in. Bye bye. Take care.